Okay, in section 10.3, we're dealing with properties of chords. And remember that a chord, if we go back to our very first set of instructions on defining what a chord is a line segment that connects two ends or two sides of a circle. In this case, we have chord AB and chord CD. And one of the new theorems that we're learning is in the same circle, or in congruent circles, like if you had two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So in this case, if AB is congruent to CD, then arc AB is also congruent to arc CD. The arc designates the section of the circle. And so, if the the chord designates the section of the circle. And now I want you to think of this. If you start at the very left end of a circle and you move to the right, what do you notice happens with the length of the chord? In fact, we can even look at a circle that has been graphed to see what exactly happens. If we take a look at this graph and a circle that's been graphed on it, we can see that if we start in the left-hand side with a chord and we move to the right, each time we move to the right, what do you notice happens with the chord? I hope you notice that the chord, as it moves from left to right, gets larger and larger, and then it stops, and then it gets smaller and smaller and smaller again. You'll notice that it gets larger until it hits the diameter. And then, after it hits the diameter, if we continue, it gets smaller and smaller and smaller again. And so, if we were to take this circle, and if we were to copy it and paste an identical circle, depending on which chord we're talking about. Let's say we grab this chord right here. Now that chord is a specific distance. It denotes a certain place in the circle, moving from left to right. It's not way over here because it's not really small. It's not the longest chord possible because it's not at the diameter. We could notice that it would have to be congruent to this chord, and not only would those chords have to be congruent, their arcs would also have to be congruent. Now, I want you to notice this, that you could have this length of a chord on one side of the diameter, but you could also have the exact same chord on the opposite side of the diameter. Remember that the length of the chords goes up as you approach the diameter, and it goes down as you get away from it. So if you've got a length here, you've also got a length here. They're on opposite sides. And so if we go back to our theorem, all it's saying is congruent chords form congruent arcs. Now we're going to take that and apply it in example 1. It says that if the measure of arc AB is 110, let me write this down. Find the measure of arc BC. Now, if chord AB and chord BC are congruent, then their arcs would also have to be congruent, which means that arc BC, and you're going to have to excuse me, there's somebody mowing outside my window. If arc AB is 110 and the two corresponding chords are congruent, then the two arcs would have to be congruent. Hopefully that makes sense. Hopefully you can see this, how it's broken it up into two separate chords. We can apply the same thing to problem 2. If the measure of AC is 150 degrees, and we assume that these two chords are congruent, can we find the measure of one of these arcs? And the answer is yes. We know that the entire circle adds up to 360 degrees. We also know that if these two chords are congruent, then these two arcs are congruent. And so we can very simply write an arc addition postulate. I can say that this arc plus these two arcs, and notice they're congruent, should add up to 360. Well, just do a little algebra here. When I combine these two, I get 2x. When I subtract 150 from both sides, I get 210 degrees. Which means that after I take out this section, the rest of my circle should add up to 210 degrees. And if I divide both of those sides by 2, I get both of the halves to be 105 degrees each. Not really all that complicated. If we go to the next page, we see another theorem. It says that if one chord is a perpendicular bisector of another chord, here we can see we have chord RT and chord SQ. If SQ is a perpendicular, that was a horrible perpendicular mark. If SQ is a perpendicular bisector of RT, meaning it's both perpendicular and bisects it, then the first chord is a diameter of the circle. If SQ is perpendicular and bisects RT, then SQ has to be a diameter. The only chord, or the only segment inside of a circle that can be both perpendicular and bisect another chord, has to be a diameter. We're going to take that knowledge and we're going to use it to solve some problems. Here in example 2, we have 3 different problems. We see that in circle Q, we have BD, and we can see that BD in this first problem, we'll call it number 1, it goes through the center Q. Now, what we want to find out is, does it bisect it? Now, you have to remember the little definition of bisect. Bisect means to cut into 2 equal halves. And if it cuts into 2 equal halves, then this side should equal this side. So, we can try and set them equal. And if we solve for x, we subtract 3x from both sides. And when we do that, we get x equals 7. So, if I plug 7 into both of these x's, I get 28. 3 times 7 is 21, plus 7 is 28. So not only does BD go through the center, it also bisects these 2 halves. We could go through example 2, number 2, and number 3, and do the same thing. Prove that the diameters both bisect and are perpendicular to these chords. You're going to find out that as we go through, we find out different properties about these chords, and the reason we need to know those is it helps us with, in this case, dealing with perpendicular, knowing that the diameter is also perpendicular to chords. If we look at our red line being our diameter, it's perpendicular to chords, but it also bisects them. We have equal amounts on both halves. If we go back to our notes, go to the next page, and we have a new theorem. It says if a diameter of a circle is perpendicular to the chord, then the diameter bisects the chord and its arc. Now this is a little bit different, and simply because not only do we find out that if a diameter is perpendicular to a chord, much in the same way the previous property said, where we have a chord being perpendicular to the diameter, if a diameter is perpendicular to a chord, it not only bisects the chord, but it also bisects the arc that it cuts across. We have here chord DF And so the diameter of this circle, EG, not only bisects chord DF, but it also bisects arc DF. A little bit different property here. So we can even read this. If EG is a diameter, okay, and it's perpendicular to DF, which we just talked about, then HD, talking about this half of the chord, and HF, talking about this half, are congruent, and arc GD and arc GF are both congruent. Now, find the measure of the indicated arcs in the diagram. What I would like you to do is pause the video, and I would like you to find the length of arc CD. I would like you to find the length of arc DE. And I would like you to find the length of arc CE. Using what we know about diameters intersecting chords. Pause the video and solve those now. Hopefully you had enough time to solve for not only X, but also the 3 arcs. Here you can see that I set 9X equal to 80 minus X. The reason I did that is I saw that BD bisected CE. These two little congruency symbols tells me that CE has been bisected. So, not only does a diameter bisect the chord, but it also bisects the arc, talking about arc CE here. And so, if CE has been bisected, then this half should be congruent to that half. That's why I set them equal to each other. Well, when I solve for X, I got 8. Forgot to get rid of my 0. Kind of a big problem. But then when I plug in 8 into both of these sides, I find out that CD is 72, DE is 72, and CE, which makes up CD plus DE, gives me 144. Go to the next page, and we find out Theorem 10.6 says, in the same circle, or in congruent circles, again, 2 chords are congruent if and only if they are equidistant from the circle. This kind of ties back into our very first theorem that we dealt with. If you have 2 chords that are congruent, they have to be congruent and equidistant from the center. If I erase all this because it's getting in my way. There we go. Now, let's say that we randomly grab this chord and this chord. Looking at these 2 chords, we can see that they are congruent. We can see that this one in this case is 1, 2, 3, 4, 5, 6, and roughly 7. This one is 1, 2, 3, 4, 5, 6, and roughly 7 if you count the little pieces on the ends. So if they're both 7, we could say that they're congruent, but we also notice that they are both 2 units from the center. They are the same distance from the center, therefore they are equidistant from the center. This theorem says that if you have 2 congruent chords, those chords are the exact same distance from the center of the circle. And we already knew that. We knew that as you move closer to a center, the chord length goes up. Once you hit the diameter, those chord lengths go down. And the diameter is the highest or the maximum length of your chord. Now you're going to deal with graphs that look like this in Algebra 2, so it's a good time to start getting used to them. Okay? But you'll also notice that if you pick a distance over here, let's say that distance is shared on the complete opposite side of the diameter, and you'll notice that they are the same distance from the diameter. And this, in our diagram, if CD is congruent to AB, then both of those have to be equidistant, meaning that EF has to be congruent to EG. Not only, and I want you to think about this, the straightest or the shortest distance between 2 points is a straight line. But not only should it be a straight line, it should also be perpendicular. The shortest distance between 2 points is not only, like if you look at these two, it's not only a straight line, but it's also a perpendicular line. Okay? So when it says that EG and EF are congruent, it also means that they are perpendicular to their original chords. That distance that they're talking about from the chord to the center is a perpendicular distance. Pause, recording, re-record. So let's go to the next page. Pause, recording, re-record. All right, let's review the different theorems that we've talked about. So far we've talked about that congruent chords inside of a circle form congruent arcs. We've also talked that congruent chords must be equidistant from the center. Now you need to remember that that equidistant part is dealing with perpendicular marks. Then we also talked about if you have a chord inside of a circle and it is bisected and perpendicular to another chord, that the perpendicular bisector must be a diameter and go through the center of the circle. We also found out that if you have a diameter, it will not only be, if it bisects a chord, it will not only be perpendicular to that chord, but it will also bisect the arc formed by the chord. Now, just like in a lot of the other sections and chapters in geometry, we're dealing with a lot of congruencies, which means that you're going to be setting a lot of stuff equal to each other. Okay? So let's take a look at your homework now.